I welcome all to our Nano Lecture series, and also the people, I want to welcome the people from the NIR Consortium, because this is a lecture not only for the Nanotechnology Health Implication Research Consortium. Of course, we have people from EPA and other regulatory bodies in the US, and some people from Europe, and even people from Singapore. So it's really a great pleasure and honor to have Thilo Hofmann presenting today. We've been talking about having him to come to Harvard for quite some time. And this is a very interesting topic, not only for environmental health and safety implications of nanomaterials, and I'm sure we'll hear a lot from Thilo, but also for emerging contaminants. I mean, we live in an era that there are new chemicals. I mean, in the US alone, there are 4,000 new chemicals synthesized every year. They make it into the market. Very few go through toxicological screening, as you know. There are also a lot of materials, advanced materials beyond nano, a lot of horizon materials that they will make it into the market and nano-enabled products in the near future. So we really need to understand the human population exposures to all these chemicals, nanomaterials, etc. And I think that's an area that for nano safety is lagging behind. It's primarily because not so much funding is in that area to understand a little bit the releases of nanomaterials and chemicals from nano-labeled products, and also quantify the human population exposure. So, and we still, unfortunately, in nano safety research, we try to answer the risk questions based on toxicological data, and we all know that to answer risk questions, you need both exposure and hazard assessment data. Thilo, I will keep my introduction to his research to his research very short. He's University of Vienna, of course. He's a professor of environmental geoscience. He was also the chair of the environmental geosciences in the University of Vienna and vice dean of the Faculty of Earth Sciences. So he's well known in Europe. He participates in many nano safety consortia and a well-known figure on fate and transport of engineered nanoparticles. So very pleased having you here, and look forward to your lecture. Welcome again, and look forward to your seminar.
Thank you very much, Phil, for this very kind introduction. Thank you for being here during lunchtime, and it's a great opportunity for me to be actually the first time at your school, so I was looking a long time for having this opportunity, and I think last time we talked in France about this. So the talk will be from my topic about vulnerability groundwater resources. Groundwater is mainly used in many parts of Europe, not so much in the US, but it's becoming more important recently. I will talk, of course, a little bit about emerging contaminants and a lot about nanoparticles. So that's what the center here also is about. And these are the last speakers. So this is a little bit CV from me. So that's the talk. So let's get started with Vienna first, because I was talking with Phil. It's a nice university over there. It's quite an old university. It's, in fact, the oldest German-speaking university in Europe, 652 years now. It has a lot of students, I will think too much, 96,000 students compared to faculty. No tuition, that's one of the reasons. No entrance fees, yeah, so no tuition, it's quite important over there. About 10,000 staff, 180 studies. And it's also a pretty nice city. I don't know if you had the chance to be there. If yes, you know it. If not, then you can see right over here the old places. So it's a huge old Habsburgian city at the times when Austria was a large country, a large empire. Now it's only 8 million people, so it's pretty small. And there are a lot of leisure activities also. That's my girls climbing. So that's the whole family over here. Some of them at the moment at Duke University, where I'm a adjunct professor also. So it's a nice place to be. And of course, I will start with a big thank you to my group. So especially senior scientists in my group and postdoc for a long time, Frank Vonnekammer, Melanie Kashi has been here giving a talk, and a lot of postdocs in my groups and PhD students who contributed to a lot of the works. I will show some pictures later. Okay, that's the outline. I will start a little bit about water resources and groundwater. Then I would like to go to nanoparticles as emerging contaminants. And then finally, I will take a good time to talk about nanofate. How do they behave and analytics. And is there a way forward? Can we combine modeling with field data? Because I think there is a gap so far, and this gap really needs to be closed as sooner than possible. So what is water about? Okay, we know that if you look to the UN Sustainable Development Goals from 2 years ago, if you look to zero hunger, if you look to clean water, if you look to life below the water, that's all linked to water. So we are all sure, and a lot of things about public health. I'm teaching basic hydrogeology at my classes in Vienna. When I start with health. Many health issues, of course, worldwide are linked to water. So water is important, that's no question. And if this water is vulnerable or not, it belongs, of course, to the question, where is it coming from? Is your river water coming from this nice river over here? How do you treat it? Is it a pond or a source? Is it infiltrated in the aquifer? And what type of aquifer is it? Is it a basement rock, fractured rock? I will talk about this later. Is it a limestone? Is it a karst, like the city of Vienna, for example? 1.6 million people get the water out of karst. Or is it from sandstone? So we will talk a little bit, not too much, about these different reservoirs and about vulnerability. And then, of course, we know the conventional threats to water, like manure over here, farming. We know industry. We know accidents. I don't want to talk too much about this because that's clear. And we know the emerging contaminants. So what is emerging? There are different definitions on emerging. There's no such thing like one definition. One point is the analytical concept. So not detected before. We just talked about 4,000 new chemicals in here. If you think to the EU in the REACH, above 1 ton is regulated, but a lot of chemicals are below 1 ton. So a lot of our chemicals are not regulated. And then detected at a much higher level than expected. Thinking about nanoparticles, well, we have problems with detection. Still, we're working on this for 15 years. Still, we have a lot of problems. And then if you look to the US EPA, risk to humans and the environment may not be known. And that's well, nano is pretty much clear. I mean, we know pharmaceuticals, P4, PFAS, personal care products, brominated flame retardants, and of course, I would say the good old nanoparticles. That's the new emerging field. I don't talk about nanotech and all this too much here because this would be strange. Yeah, this is the Center for Nanotech, so you all know about this. I would add another 3, 4, 5 slides in a different community, but not here at this talk today because you all know about this. So let's start with hydrogeology, and I jump right into it. What you see over here is a waterwork, okay? This nice red thing over here, that's a drain tile. And this over here is an aquifer. And this small waterwork over here feeds one of the major cities in southern Germany with drinking water. I'm not allowed to release the name. They drink a lot of beer, especially in October, but the name you will not hear from my side, okay? So the interesting point maybe for you is that the water is not treated. It's not chlorinated, nothing. It goes into the pipe, right, like you get it out of the aquifer. That's it. And they do it for a long time. And the stomachs, I don't think they're so different than other stomachs in the world. So they live quite well off this. So a question mark is over here. Here you see a river, okay? The river is crossing over here, question marks. Is the river infiltrating? We don't know exactly so far. But this is about some, let's say, 2 to 3 kilometers, so the water might be well filtrated. But what about here? Here the river is coming pretty close. Is the water infiltrating over here? And what happens? Especially, you know, what happens during flood situations? During flood situations, yeah, sewage water impact is completely different during flood situations. So is this waterwork basically affected during this stage or not? This was the question the guys asked to us, and we should basically investigate it. And they also asked about, do we have a risk that nanoparticles, they haven't heard about so much about nanoparticles over there, but what about nanoparticles? You know, the public is aware of this, the public asks, and it's a public company, so they ask, guys, we want to know, what about nanoparticles? Do they enter it, or microplastic? Do we have microplastic or beer? You know, there are these fancy publications about microplastic and beer. Well questioned. So the question here was, nanoparticles, do they enter, yes or no? So what do? We can't, of course, put a nice, I don't know, a glass window up here and look to it. So we thought, let's emerging. So the 2 tracers we were using is, the one is acesulfam. I don't see a diet or zero Coke over here at the moment. But when you drink Diet Coke, the sweetener used in the US partly is acesulfam potassium. In Europe, acesulfam is the dominant sweetener. In the US, sucralose is used more. In Europe, it's more acesulfam. The companies are on off with these different sweeteners, but they're used in an increasing amount. So acesulfam is a tracer for us because it's an indicator of wastewater. And then we know how much of this tracer do we find in the drinking water? Is there a wastewater impact to the drinking water? And another interesting guy is gadolinium. Why? Because you have an MRI contrast agent, of course, and the use of gadolinium is ever increasing. At least definitely in Europe, I know the data. For the US, I don't know the data, but I think it's pretty much the same. And I just downloaded 2 days ago this warning from the US FDA, gadolinium-based contrast agents, drug safety communication, retained in body. So the problem with gadolinium is if you look to these complexes over here, these are more the new products on the market. New is, let's say, 10, 15 years. But there are older products on the market for MRIs, which are linear complexes, and the linear complexes are much less stable. So if you get your next MRI, be very careful what you get. The linear complexes, I would say, nope. These are the modern complexes. The complexes are super stable, and they are charged, of course, negative because you excrete, after you get your MRI, you excrete the gadolinium complex. If your kidneys are okay, within 24 hours completely. So we said, okay, gadolinium, this would be a suspicious substances to look for because the concentration should directly give us information about how this looks in the groundwater. And so how do we analyze it? We're using triple quad ICP-MS. That's Robert. That's the guy who's doing this. We developed it for quite some time because for normal metal, it's a rare earth element, the detection limit had to be down to 0.04 nanograms per liter, 0.1. Those of you working with metals know that that's a terrible thing to achieve. You need to boil all your liquids, all your acids, treat every vessel you're talking around. You have to be careful with room dust and everything because else you have the contamination. And then we measure only total gadolinium, okay? But in Earth, we also have the rare earth elements naturally. So we can't measure the natural one. So what we do is basically we just do a bracketing. We measure the neighboring samarium and terbium. And that's the reason why we need this very low detection limits. And then just by knowing these neighbors, by this nice up-down pattern, which you have always with rare earth elements, you can calculate the geogenic gadolinium, which is not so much. So you can then basically at the end say, okay, my anthropogenic is just the total measured minus this little gadolinium geogenic. And this works excellent. So you get pretty good values for these gadolinium. And with this data, we went now into the aquifer, and there are the two things. They both show totally the same. This is the sweetener, acesulfam. I explained it with the gadolinium. So the first thing what you see over here is, oh yes, it is infiltrating. And there we get the gadolinium right into the water pipe. That's not so much frightening because it's a long distance. The water still has to travel. But look over here. What you see here is you got concentrations which are increased, which means the groundwater over here also has the gadolinium, which is a very specific sewage water marker. So the river is infiltrating. Why is it infiltrating? Because the waterwork is pumping out so much water that the water level is lowered. So the river is infiltrating here inside the aquifer. And during storm events, there's a risk that the water can enter over there. Of course, we did some modeling. I cut this short. I don't want to talk too much about groundwater modeling. But during a storm infiltration session, when we did the modeling, we can see, yes, here are the path lines of the groundwater. So the groundwater during storm events is entering directly from here, the drain tile. And the color is red, which means the residence time is something like 3 days. So this is very fast. So yes, this waterwork might have the risk for these emerging contaminants to enter. So, and there I switch basically to nanoparticles as emerging contaminants because for the guys over there, this might be a topic at least to be aware of. So you know all these products on the markets. You have, as I heard, changing a lot from implications also to applications. One thing, Melanie gave a talk here 2 years ago, I think, was on agricultural products. Very interesting. We were doing a lot of research on this. We just started a research project together with Carnegie Mellon University and University of Kentucky nanofarm on applications of nanopesticides to land. Why? Because now you have nanoparticles which you release by purpose, and you have something toxic on it. So that's an interesting thing for environmental scientists. So since the last talk from my group was about nanofarming, I stick a little bit more with this application over here, Sunscreen, and I show you some data on this. So a project we were working in is just like, this is Andreas Gondikas. He was before at Duke, and now he's in Sweden. Between he was 3 years postdoc in my group. So people, of course, use sunscreen. And in modern sunscreen, you have nano TiO2, which has typically a small coating with aluminum oxide. And then we thought, okay, if everybody is very consensus and uses a lot of sunscreen, yeah, and it goes swimming, then the sunscreen, of course, should wash off. There is no data on this. We searched the literature, no data. So what we had to do, we had to ask quite a few students, guys, can you put some sunscreen on it, go at home in the bathtub, take some water before and afterwards, because there is no data of how much of the titanium releases. So we had a lot of fun with this, did some nice calculations, some different scenarios, which can be read in the papers. And the last one was just getting out a few weeks ago in Environmental Science Nano. So this was the idea why we wanted to look to this. But what is the reason? Titanium is a natural product. It's a mineral which you find abundantly in Earth, so that's nothing special. We did some studies a few years before on biofilms. This is a flume fed with pristine river water. And on the river water, we grow biofilm to a certain stage, not to this one, to a stage like here. And then we dosed in the beginning here of the flume a very low concentration of nanotitanium, a concentration being found also at the outlet of wastewater treatment plants. And what we saw is we did some staining tests with cyto13 and propylium iodide. This is a live dead kit. So basically with the red ones, with the propylium iodide, you see compromised cells, and the cyto colors all cells. Data shows you that if you look after 48 hours over here, the control sample to the P25 from Degussa, now Evonik, or the Hombicat, two catalysts which are mainly used, then you see that you have significantly more compromised cell walls, even at this very low concentration. So this was one of the first papers showing that at this very low concentrations, you have an effect on the cell basis. And then we said, okay, let's go back to Vienna. This is the city of Vienna. Right inside the city, about there is my institute. And this is the old Danube. The old Danube now is only a lake. There is no water flowing. Yeah, it's just a lake. And we have people like sunbathing over there. We have 1 million bathers a year. So that's a high exposure scenario. And of course, they don't go swimming in winter. Yeah, they're not crazy. So it's just the 3 or 4 months when the people go swimming. So we have a high input scenario. And we thought, if not there, where should we find the nanotech? So we gave it a shot. The idea was, if they use the sunscreen, look to these two pie charts over here. In the sunscreen, you have a lot of titanium and only a little bit alumina coating, so the titanium to alumina ratio is pretty high. In natural particles in the soil, you have a lot of everything, so the titanium to alumina ratio is very low, 0.04. So it's a lot of aluminum and only a tiny bit of titanium. So we thought our handle analytically could be this titanium to alumina ratio. We compared here data for the no bathing season and for the bathing season, and can see, well, yes, it is elevated, not so much as we thought, and I keep this a little bit short. Where does it end up? Of course, it ends up in the sediments. So we used the sediment cores, we were doing coring, we compared samples from the lake, blue, to the reference lake in red, and we could see over years we got an increase in this ratio, and then together with the EAVAC, we did some SEM analysis, automated SEM analysis of a few thousand particles, and also found these guys over there. But it is a ratio. It is not really proof. So we have to go a step further. So what about the fate? So that's all the story about where we are working. We are a lot of working about environmental fate, and that's where I want to dig a little bit more into today. So my colleague Frank von der Kammer, he's working on a lot of EU projects, brings in a lot of money. It's a great scientist, and some ideas from him over here. So where does the nano go? I mean, people in this group are working also a lot of air. They're working in different fields. This is a nice picture which I steal from Kendra Garner. I stayed in the group of Arturo Keller last year for 6 months in Santa Barbara. So you have a lot of different things over here which are quite complex. You can try to include all this in the model, make the model more complex and whatsoever. And I just said, for me, working in aquatic science, so there are a few things which are dominating. For example, aggregation and the flow and the suspended sediments and heteroaggregation. Dissolution, it's very important, overlooked. And then also here in this picture, there was sorption. There's no such thing like sorption of nanoparticles. It's attached. There, we published 3 or 4 papers just having a big fight and debate about there's no sorption of nanoparticles. It's not a thermodynamic equilibrium process. It's attachment. So I wanted to look in the next slides. So where does it all end up? And how do we get a grip on this? Because you have all these processes and factors involved. So you have the extrinsic properties, pH, water chemistry, NOM, redox, et cetera, the intrinsic properties, composition, surface charge, hydrophobicity. You have transport inside the aquifer in the groundwater, or we have transport in the river. We published a paper here. And so basically, to make it short, in the aquifer or in the soil, they stick to soil. And in the river, they heteroaggregate with suspended particulate matter. So that's where they end up. So how did we get a grip on the rates? How do we debunk all this? So modeling, you can come from 2 sides. You can start here at the process scale, on the pore. For example, particle aggregation, there are nice models, University of Geneva, Serge Stoll, with you can tune a little bit on the Hamaker constant to tune attachment rates whatsoever. But you need a lot of parameters to run these models. Or you can start at the totally different scale. You have unit world large models. You have these boxes which you combine. Sure, like material flow models, you have a maybe high uncertainty. I wouldn't say the uncertainty is low here. You can have regionally spatial models. So these models down here, they're very good for process understanding, but a huge parameter demand. And can you upscale this? And what are parameters which are transferable? Is it possible to upscale it? I would say in many or in most things, it's not possible to upscale this. So is there a sweet spot for the modeling or not? That's a question. And there are a lot of models on the market. We work at the moment in a nice large project, Nanophase. Amy Dale, I think she's now working here close by at MIT. Arturo Keller, Lavenza was working this. Antonia Pretorius, she was from the EDH, now working in my group, and now leaving to Tokyo in a few weeks. So a lot of models on the market, but there is one thing in common, that they depend a lot on simplification or complexity. And let's get a little bit into this. So what I want to do is talking about debunking surface water chemical reactor. This could also be, for me, it's a surface water or groundwater. It could be for you just your media you want to run your experiments. So you have a lot of constituents in your water, yeah? So it's a pretty complex mixture. And then how do we get a grip on this? We can look, so what is known? This is a map of Europe. In Europe, you got the nice database, the Forex database, with all water chemistry of all European rivers. We know that there's a lot of variations of parameters we don't understand, like NOM or various particles, for example. And do we really have to take this into consideration? And then we can reduce this to relevant water chemistry and make this simpler and get a simpler test. And from there, we can say, okay, we know that calcium is dominating over sodium. We know the pH is important, NOM is important. We know that calcium is more or less equal to magnesia, and so on. So we can make, at the end, a very simple water chemistry, which I would like to call relevant, because realistic, it's close to impossible to run test scenario with these set of parameters. They're going to infinity, the parameter sets, if you include NOM. And that's a starting point where we developed basically an OECD guideline, which is the first guideline published by OECD for nanoparticles. So we used existing public database for water chemistry. So we used the database here, which we got from Europe. And then we designed the test and made this very simple. And it might sound stupid, but we just said, okay, we cover 90% of the natural conditions in all rivers in Europe with no more than 3 variations. So we just take pH 5, 7, 8.5, calcium 0, 1, 10 millimole, NOM, O and 10. We take a standard type of Swanee River NOM. It's not better or worse than anything else. There's no such thing like the NOM. Yeah? All are different. We can discuss hours about this. And then we make a very simple test approach with the dispersion step, aggregation step. And then you can do a quick testing, basically, where you just see the stability, or you can do this over a time series. And this ends up in the OECD TG 318, which was published last year by the OECD. And we did it actually in our lab. So our lab was a contractor for the German Environmental Protection Agency to do this first guideline, which standardized test methods, particularly for nanomaterials, adopted by the OECD. And the very principle is we run a very simple test with a reduced amount of different hydrochemical media just to get a snapshot and to understand and to give an input to the models, basically, an educated input in gas, how stable are these particles. So we can differentiate initially between particle type A or C and AB, at the end between A and BC, and in the middle O. It's nicely written in the guideline and in the papers. So the result basically are these simple things, stability plots. So you get your titanium, for example, or whatever material you want, with NOM, without NOM. That's one of the driving forces. And then you just like the percentage of particles being still in dispersion or not. And you get very fast stability plots. And the point is here, and we published a paper just, I think, 2 or 3 weeks ago, what is the scientific rationale for the development of such a simple OECD test guideline? We think it's important to do so because to do a step forward, why the test needs exactly 7 hours. Why 7 hours? Because that's a lab day. Yeah, preparation, reading a little bit. So the test procedure, 6 hours measuring, and then it's 7 hours. You can run a lot of samples automatically to get these data, which is not available. And that's also something what companies need if they are in production, want to produce different type of particles to run these tests pretty quick. One thing is a lot needed to improve. We need to improve the work between the models and the laboratory. We are strongly on the laboratory side. And the validation of models with field data is much needed, as well as design of experiments guided by these modeling results. So at the moment, I got the feeling that sometimes this is working a little bit side by side, but not jointly. So the combination of modeling and field data of analytics is important. So this comes down to a question. We need reliable field data to validate the models. And this means we need analytical tools and concepts. There we are not so good at the moment. Yeah, there's something we have to improve. And I show a few things where I think there is a window of opportunity to go forward. So what is the nanometrology challenge? So basically the challenge is if you have a clean laboratory situation, well, that's boring, even for the target analyte. So for example, gold, silver nanoparticles in pure water. That's nothing special. Everybody can do so. Analyte alone in a natural environment, like out in a river, in the soil, heads up, this is getting more complicated. Like fullerenes, nice techniques available, spectroscopy, current nanotubes, this is an M, not an M, copper and zinc. So that's possible, but it's getting a little bit more complicated. And here it gets really interesting. Analyte among similars and its natural environment, so far close to impossible with conventional techniques like silica, titanium, iron, cerium, or organic nanoparticles in the environment. How do you do so? How you tell the regulator later, this particle there is engineered, this is natural. And the best thing is to this is engineered from BASF. Yeah, this would be the best thing. One step forward would be, of course, you force BASF to label the particle isotopically. Guys, you believe they love to do so. Of course not. So we need a handle, we need something to analyze later ENPs in a river, in the environment, and really to tell, okay, this is natural engineered. To just get a grip on, do these exposure models are within an order of magnitude, or 2, 3, 4? How many orders of magnitude are we in or out? So this is still missing. So this is an open question. So one thing, what we drive forward, this is Manuel Montaño. He's from Colorado School of Mines. Then he was at Duke University. Now he's in my lab in Vienna, and he's working on a time-of-flight mass spectroscopy. We just bought one of these machines a year ago. There are not so many labs having these. I think it's only 3 at the moment in the world. running this single particle time of flight. Not time of flight, that's well known, but doing single particle time of flight mass spec. So what is the thing, basically? We are doing single particle MS, so at very short acquisition times, basically, in the plasma, we inject the particles, and then we ignite particle by particle in the plasma and get the full element spectra in the TOF MS, basically, over here. And the idea is that with a single particle ICP TOF MS, that we can do nice things, and this here at the top is something we can do at the moment, like core shell particles. That's possible, or we can identify particles that have a distinct pattern. We can analyze at the moment ENPs and natural nanoparticles with a distinct element ratio, like cerium. I will show this to you in a minute. And here we come down a route where we don't know if it ever will be possible. For example, engineered nanoparticles and natural nanoparticles with near identical elemental composition, isotopic composition. Maybe possible, NOMs in coagulation, I don't know at the moment. So at the moment we are here, we want to go down further. So what's the thing? I show you one of the papers. Antonia is first author, but it's a multi-author paper together with the ETH Zurich. We were looking at cerium oxide nanoparticles in soils. And same thing again. There is a distinct ratio between cerium and lanthanum in the environment. The cerium to lanthanum ratio in the environment is around 2. And we have river sediment samples from all over Europe. You can plot them. It's a straight line correlation because the formation is at the same time geologically, not time. It's basically when the magma basically cools, you've got the co-precipitation of these two phases. And this is, of course, completely different than cerium oxide nanoparticles, which are used from catalysts or abrasives or polishing material, because that's pure cerium. While the natural particles, they have a cerium-lanthanum ratio. So here we go, what we can do with a TOF MS, what you cannot do with a standard quadruple. So you can see basically with a TOF, of course, 2 elements at the same time. So you see, okay, here I get my cerium, and here I get my lanthanum. So I can say, okay, that's a natural nanoparticle. They both come at the same time. And you can say, okay, that's the pure cerium spike over here in the ICP-MS in the plasma. So that's my engineered nanoparticle. That's the idea. And we run these samples, and we get a lot of spectra and analyze these spectra and check for the detection limit. So far, we came down to a limit of 0.4 milligrams per kilogram cerium oxide spiked and added, which is 0.5% of the background. So we can go pretty low down to a background of cerium. The background of cerium is not high. And we can go down to 0.5 of this background and still analyze engineered cerium oxide nanoparticles in the environment and make clearly sure this is an engineered nanoparticle, this is natural, this is engineered, exactly what we wanted to do. And of course, the next step is combining this and automating this. So we did some automatization, we did some machine learning at the ETH Zurich for automated identification. Basically, what we did is first we considered not only 2 elements, but 27 different elements. And then later we selected 17 of them. And then in machine learning, I'm not a machine learning guy. This was the guys at the ETH Zurich. So we had these training features. We had the training part of the data set. We trained the model. The trained model was then later used for the classification of our code. And this worked quite good. If you look to the next slide over here, important is basically these orange color uncertain. And then all these bars over here, this one, the last one, that's the machine learning automated separated data. And what you do is compared to manual separation or analysis where you decide, you get a little bit rid of the uncertainty. So you get a classification, engineered versus natural nanoparticles, yeah? And even at low concentrations, here the concentration is increasing in this direction, you get a pretty good classification here and a low uncertainty using these machine learning. So you can do this fully automated, basically, which is a nice thing. Okay, some other things you can do, for example, here on the left side, you see a classical single particle ICP-MS, a quadruple. And we analyzed for core shell particles, gold and silver. So the problem is here you have the gold signal, and here you have the silver signal, but you can only switch between the 2 elements. You can't measure them simultaneously. So if you do so with a classical quadruple ICP-MS, and here these particles, these are core shell particles, gold, silver, core shell, you don't find them. gold, silver, core shell, you don't find them. Either you detect them as silver or as gold. With the TOF-MS, it's different. With the TOF-MS, you can analyze all the elements at the same time. And these here in the violet color, these are silver gold core shell particles. And of course, you would nicely find them here with the TOF-MS, and you can separate these core shell particles. Or a last example, basically, what you can do is, this is platinum in a time-of-flight mass spec. And the time-of-flight mass spec also enables for isotopic quantification of enriched particles. Not of environmental isotopic fractionation processes. There you need a multi-collector. But if you have enriched particles, you can nicely separate here, for example, between the different platinum isotopes, which might help in some studies. Yeah, we are just starting, honestly, to play around with these samples and play in a lot of environmental samples with this technique. Okay, and that's the logical next step. We are working in the nanophase project. That's the PhD student, Helena. And the next step is, of course, we want to work with complex systems with heteroaggregation. We set up things now. We did the OECD guideline for homoaggregation, knowing that heteroaggregation is the driver. So that's what we do now. We want to go for a simple model with simple flocks. We want to look how representative is this to make at the end something which I would call informed simplification for a functional assay. So we want to come up with the same thing with a functional assay at the end to estimate heteroaggregation or modeling with informed simplifications. If we succeed, I don't know. Ask me in 2 years. Maybe, maybe not. I mean, Helena, of course, thinks yes. So, we will see at the end of the PhD thesis. Okay, to close this up, back to nanorisk and water. What does this all mean, nano, for our drinking water safety? Is it now safe or is it not safe or whatsoever what we talked about? The answer depends a little bit where your drinking water is from. And so if you take rivers, a reservoir, it's a very trivial answer. It depends the risk on the treatment step. So we did a lot of different modeling approaches, which you can read in the paper here if you're interested in water research 2 years ago, 1 year and 3 months ago, actually. And you can combine different inputs from wastewater treatment plant, from leisure activities, surface stream, sedimentation, whatsoever. At the end, the point is, it really depends on your treatment step. How reliable is the treatment step? How reliable is the membrane? Is the integrity of the membrane secured? What type of flocculation sedimentation step do you have? So there's no such thing to predicting this easily. This depends really. This is in Singapore, completely different for infiltration than here in Boston, for example. So this really depends on the waterway. No simple answer on this. For poor aquifer, I allow myself to give a simple answer today. No risk in general. If. I come with the if. Of course, I'm a scientist, so there's always an if in the conclusion. So we calculated a lot of different things for sludge amendment. What is the concentration of nanoparticles in the sludge? What is the thickness of the soil? What is the thickness of the vadose zone? What is the water flow velocity? Filtration theories, yada, yada, yada. At the end, you come, whatever you do, up with 0. So in groundwater, these particles are not transported, not at relevant concentrations. The retention in the aquifer, in the poor aquifer, is just so strong that you can forget about it. I come to the if in a second. And so last thing, because more or less 1/3 of the world is fractured aquifers, so fractured aquifers are pretty much important. We just use the good old data from radioactive waste deposits. If you look to Switzerland, Grimsel Pass or Jakob Mountain or to Aspay in Norway, there's a lot of research of colloidal transport in fractures. And we used the equations from these guys and calculated basically these type of nomograms for the size, the width of a fracture, and the residence times. I give you 2 examples. If you have a fracture half width of 1 meter, so that's really a huge fracture. Yeah, that's already 2 meters. Then need something like 42 days until you get basically rid of your particle. If the particle is a 200 to 300 nanometer dense ENP, for example, you go for silver, titanium, or zinc in a low ionic strength media. And we did this, of course, for all different hydrochemistries, different particles, et cetera, in this paper. If you have a 10-meter wide fracture, this equals to more than 1 year. So the message is to be careful in karst aquifers. If you have aquifers with large fractures like karst, yeah, a lot of, I don't know, a lot of Europe, Southern Europe depends on karst aquifers. Like if you go to Croatia or Serbia, to Greece, to Turkey, there are a lot of karst aquifers, which are very important. And in Austria, 50% of Austria relies on karst water. Then basically the retention is very low because the residence time of 1 year, you seldomly find. Often the residence time is shorter. So you can calculate this and make some good predictions. Okay, with this, I would like to conclude the talk and wrap it up basically with a few key messages. So first, trace contaminants like gadolinium, I like them in a way because, I mean, they are there. So they can be even very helpful to understand environmental processes. So we like to use these these anthropogenic tracers to understand natural systems. Simple high-throughput functional assays help to predict ENP stability and allow for better exposure modeling. If you close your eyes a little bit, then it works pretty good. But I think that's really a way forward. It doesn't make sense to analyze for 100 or 200 different water chemistry. Then you will never come to results for one particle. And we have to analyze a lot of particles. The next step is heteroaggregation, of course. Analytical techniques, protocols still needed. Models so far not validated versus field data. That's really point. And I think Timeofflight MS might be a door opener. That might really be a breakthrough where we can analyze a lot of particles and get this. In general, for waterworks, current knowledge does not predict a high vulnerability towards nanoparticles to enter drinking water supplies. I would say most systems are pretty safe. There is not a risk for this if the raw surface water is appropriately treated, so coagulation, sedimentation, or filtration steps are done well and monitored, or groundwater is used. Exemptions exist, for example, karst, large fractures, fast flow with very low residence time. The examples I showed in the beginning, very fast flow, only 3 days. That's not safe, but that's very seldom such a situation. Or non or bad treated surface water, for example, membrane failure or something. And with this, I would like to thank you, and I'm happy to take questions.
We have questions. We'll start with the audience first, and then we can switch to online participants. Questions from the audience?
Thank you. Very interesting talk. I have actually 2 questions. One is, how can the model predict these new emerging nanomaterials like the microplastics? Because, I mean, I understand that your models are based on metal-based particles which have a high density and they settle down. But what about the ones which don't settle down?
Very nice, because I don't know, maybe you want to turn me, because that's exactly a paper we published last year. What did we learn from microplastic research from nanoparticle research? That was an ESND paper. As a feature, we put it out. Actually, yes, there are a lot of similarities, but there are big differences. So with this model and with this approach, that's not possible for microplastic. Because here, with nanoparticles, you have large flocks with a density, and often you have denser nanoparticles which attach, but which doesn't change the buoyancy of your particles. With microplastic, this might change completely, because often you have larger fragments. It's called micro, but often it's milli. So it changes the buoyancy, but you still have aggregation, heteroaggregation. So the processes, there are a lot of things which are simple and which are similar also. So we made a nice table. What can you extrapolate? What can you use the knowledge? And where are the differences? What you can. For example, in aggregation and flotation, it's not the same. It's different. You can't use this for microplastics one-to-one, but you can learn for it. And you can use it for denser microplastics. But that's research which is currently ongoing. I didn't show the research in my group because I thought, okay, 45 minutes, that's enough slides for 45 minutes. But part of the group is working with sorption, desorption, and part of the group is working with nano, and the third part of my group is working with microplastics. And we're doing a lot of leaching, basically. We are looking to additives like phthalate or other substances from microplastic, how they do basically behave in the environment. You had a second question.
Source are mostly like from sunscreens, from farm, like used as pesticides. But recently there has been increase in the use of engineered nanomaterials in filtration plants itself, water filtration plant or refuse filtration plants, which are processing the water which is going back into this aquifers perhaps. So there has been a lot of studies going on. So if you have some ideas about that.
And the question is exactly?
It's about the source, because in your studies, you are basically using the source that is coming from the consumables.
The source of the reusing.
Yes.
Is, well, it would be very interesting for me to learn about the discussion in the US. I studied Technical University Berlin. Berlin, depending on the weather or if there is a world championship in football or not, they have up to 70% of reused water. Because it's a large city with a very slow flowing river. So the lake over there basically receives the wastewater and with the particles inside, and then it's basically reused for drinking water, and it's up to 70% reused water. I'm not sure. It's a gut feeling. And I don't know what the discussion in the US is, because what they want to do in Germany and also in Austria is, and in Switzerland, they're talking about the first stage in sewage water treatment, wastewater treatment, which means filtration of the water, ozonation for the water, basically end of pipe, complete treatment at the wastewater treatment plant to get things out over there before it enters the system. It's a multi-million thing, and it will need maybe 20 years or something, but that's the discussion and at the moment, and it's very vital, the discussion. There was just 2 weeks ago a big article about multi-resistant bacteria. Well, of course, that's the thing. And where do you catch them? Is the hospital over there responsible, or is the sewage water treatment plant responsible, are the user responsible, and where should the treatment take place? And that's the thing about these fourth treatment step. My feeling is, before we have this treatment step, is that let me wait another year maybe to give the correct answer. Heteroaggregation is here so dominantly that different than for polar pollutants, which are enriched in the systems, I wouldn't guess that microparticles are so much enriched. They're enriched in the sediments. In the sediments, you will see that over many years there was nothing, and then really it's increasing the different particles in the sediments. This will be the final sink. So I don't expect an enrichment. I would expect that you see the enrichment for the polar compounds, which are non-degradable.
Follow up on that topic. There's a big difference between New York and Boston, and then all the cities along the Mississippi. And so again, the Mississippi water, I think I was told that, water comes in and out of the Mississippi River about 5 or 6 times by the time it goes out into the Gulf. In contrast, we have New York and Boston have sheltered watersheds that are 50 to 100 miles from here, and the water is very, very clear and clean and doesn't need to be treated very much. My question is, you emphasized materials, nanoparticles coming from people. How does that compare, such as sunscreen and gadolinium? How does that compare to traffic-related pollution, cars and trucks? There's zinc nanoparticles in tires, and tires disappear. Power plants, incinerators. What are you finding in the Danube? What are the major sources of nanoparticles?
Well, first is of the engineered nanoparticles, people don't know. That's the correct answer all over Europe and also in the US. So you get an idea from the emission models, but that's still emission models. And there, of course, traffic plays a dominant role. I know a little bit more for tire wear. We just, it will be out next week. We just finished a review paper for tire wear and microplastics. Because it sounds strange, I would say that tire wear, it's a well-investigated topic for decades, but not what is the role of tire wear as microplastic in rivers or something. It is really overlooked. And we just dug into this and are doing some analysis, and it's a huge fraction. It's a huge fraction coming out of traffic compared to the consumer products on nanoparticles, which are used, like say, personal care products like sunscreen. I would say that the personal care products are not dominating, but that's a gut feeling. Point is I want to make is, at the moment, nobody is able to analyze this correctly in the environment. So it is modeling and guessing. We just don't know. That's the reason we have to drive further analytics, because you can make a lot of the discussion what's ending up in the reservoir, what's there. It's still a modeling approach, a life cycle modeling approach, but you don't have the proof if your model is correct. We don't have the validation data so far. So that's where we have to go.
There's a tire consortium, and I think they have found a particular component of latex, of rubber, which is sort of a signature for tire, for particles in water. And again, they emphasize the fact that often roadways are next to rivers,
right,
and so on.
Right. And you always have the water, which is basically then collected and going directly in the rivers. And then more recently, I think the last 10, 15 years, this road runoff is not allowed to flow directly to the waterways, but has to be in these filtration ponds first. But most of the roads are not, just filtrating directly.
Boston is very strange. We take all our wastewater and we put it in the ocean, which is really something.
It seems to be it's close by.
It's convenient, but what it means is that the rivers are often depleted during the summer because they pump out some groundwater near the rivers and then don't return it at all the way you're doing.
Right.
The audience? Any questions from? Okay. All right. Thank you, Thilo, for a wonderful presentation.